There is a question that sounds simple at first, but the longer you sit with it, the more it quietly expands. Why is the universe so empty? Most of space is not just quiet. It is almost entirely empty, not partially empty, not sparsely populated, empty in a way that is almost impossible to hold in the mind. The distances between things, between stars, between galaxies, between the vast clusters of matter scattered across the observable universe are so immense that matter itself becomes little more than a faint suggestion against an overwhelming background of nothing. Tonight, we will explore that emptiness slowly and carefully. We will look at what empty actually means, both at the largest scales the universe offers and at the smallest scales science can reach. We will consider why matter is as rare as it is, what fills the spaces between things, and whether empty space is truly empty at all. We will move through these ideas without rushing, giving each one room to breathe and settle. Welcome to Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and reflection. Whether you are listening closely or beginning to drift, everything we explore tonight is meant to accompany you gently. So get comfortable. There is no urgency here. The universe has been mostly empty for nearly 14 billion years, and it will remain that way long after tonight. We have all the time we need. Chapter 1. What we mean by empty. When most people think about empty space, they picture something like a dark room with the lights off, a contained absence, a place where things could be, but are not. That intuition is understandable. It is the kind of emptiness we encounter in daily life, the emptiness of an unoccupied chair, an unused room, a quiet street late at night, familiar, bounded, temporary. But that is not what astronomers and physicists mean when they describe space as empty. The emptiness of the cosmos is not a room waiting to be filled. It is not a pause between events. It is a condition so pervasive and so fundamental that it requires us to rethink some of our most basic assumptions about what the universe is and what it contains. To begin to understand it, we need to start with something familiar and then follow it outward, step by step, until the familiar falls away entirely. Consider the room you are in right now. Whatever its size, it contains air, furniture, walls, a floor, a ceiling. It is full of things in the way that most spaces in our daily lives are full of things. Even if the room were emptied of every object, the air would remain, roughly a billion molecules of nitrogen and oxygen and other gases filling every cubic centimeter of the space. To empty the room of air as well, you would need a vacuum pump and a sealed container. And even then, no pump can remove every last molecule. A perfect vacuum, in the engineering sense, is an approximation, not an absolute. Now step outside. The atmosphere extends above you for hundreds of kilometers, thinning gradually as altitude increases. At sea level, the air is dense enough to breathe, dense enough to feel on a windy day, dense enough to carry sound. By the time you reach the altitude where commercial aircraft fly, roughly 10 kilometers above the surface, the air is already too thin to breathe without assistance. At the edge of the atmosphere, 100 kilometers up, the density has dropped to almost nothing by the standards of the surface, though it is still far denser than the space beyond. Beyond the atmosphere, in the region we call near-Earth space, the density of matter drops further still. There are particles out there, protons and electrons carried on the solar wind. Occasional dust grains left over from the formation of the solar system. The faint traces of gas that extend even into interplanetary space. But the density is so low that by any everyday standard, This region qualifies as empty. Yet even this is not what astronomers mean when they describe space as empty. The solar wind, which carries a stream of charged particles outward from the sun in all directions, fills the entire solar system with a thin but detectable medium. The region within which the solar wind dominates, called the heliosphere, extends to roughly 100 times the distance between the Earth and the Sun in every direction. Within this bubble, the Sun's influence is felt, and matter, however sparse, is present. Beyond the heliosphere lies interstellar space. Here, the density of matter drops to levels that have no counterpart in any laboratory on Earth. In a typical region of interstellar space within a galaxy like the Milky Way, there are perhaps 1 atom per cubic centimeter. To put that in perspective, the air you are breathing right now contains roughly 27 billion atoms per cubic centimeter. Interstellar space contains 1. And even that 1 atom per cubic centimeter is not uniformly distributed. In the regions between the spiral arms of the Milky Way, the density drops lower still. In the hot, diffuse gas that fills much of the volume of the galaxy, densities of 1/10 of an atom per cubic centimeter, or even less, are common. In some regions, the interstellar medium is so thin that it constitutes the best vacuum achievable in any laboratory on Earth, and then some. This is the emptiness of interstellar space, and it is already far more extreme than anything our daily experience prepares us for. But we are still inside a galaxy, still in one of the more populated regions of the universe, still surrounded by the gravitational influence of hundreds of billions of stars. Step outside the galaxy, into intergalactic space, and the emptiness deepens again. Between galaxies, the density of matter drops to somewhere in the range of 1 atom per cubic meter. Not per cubic centimeter, per cubic meter. A cube of intergalactic space 1 meter on each side, large enough to stand inside, would contain on average a single atom. And that is in the relatively populated regions between galaxies in a cluster. In the great voids between galaxy clusters, the density is lower still. There is no human-scale analogy that does justice to this. The best we can do is note that the emptiness of intergalactic space makes the emptiness of interstellar space look crowded, in the same way that the emptiness of interstellar space makes the emptiness of a laboratory vacuum look crowded. The universe is empty in a way that scales. Each step outward, from room to atmosphere to solar system, to interstellar space to intergalactic space, reveals a new order of emptiness, a new level of sparseness that exceeds the previous one by many orders of magnitude. And this raises a question that is worth sitting with before we move on. Why do we find it so difficult to intuitively grasp this emptiness? Part of the answer is simply that our brains evolved to navigate a world at human scales. The emptiness that mattered to our ancestors was the emptiness between trees in a forest, between water sources in a dry landscape, between members of a social group. These are all scales at which matter is relatively abundant, at which the density of meaningful things is high enough to reward attention. Our intuitions about space and distance and the distribution of things were calibrated in an environment where the emptiness of intergalactic space is not just irrelevant, but unimaginable. Another part of the answer is that our sensory experience of the world actively conceals its emptiness from us. We see surfaces, not the spaces within atoms. We feel resistance when we push against objects, not the electromagnetic forces that actually produce that resistance. The world presents itself to us as solid and full, and our experience confirms that presentation so thoroughly that we have no instinctive reason to doubt it. It takes deliberate effort, the kind of effort that science requires, to look past the appearances and recognize the emptiness underneath. A useful way to begin retraining that intuition is to think carefully about the nature of distance. We have a reasonable feel for short distances: a centimeter, a meter, a kilometer. We can picture these. We have walked kilometers, handled centimeter-scale objects, measured things in meters. Our bodies give us a physical reference for these scales. But consider the distance between the Earth and the Moon, roughly 384,000 kilometers. If you were to lay the Earth's circumference end to end, you would need to do it about 10 times to cover that distance. Or think of it this way. If you drove a car at 100 kilometers per hour without stopping, the journey to the Moon would take roughly 160 days. That is more than 5 months of continuous driving, day and night, without rest, at highway speed. That is a distance we can at least partially grasp, even if we cannot feel it the way we feel a short walk. Now consider the distance from the Earth to the Sun. About 150 million kilometers, nearly 400 times the distance to the Moon. That same car, driving at highway speed without stopping, would take roughly 170 years to cover the distance. Not a human lifetime. Multiple human lifetimes, one after another, of continuous driving. Light covers that distance in about 8 minutes, which tells you something about both the scale of the solar system and the extraordinary speed of light. And yet the Sun is our nearest star. The nearest other star, Proxima Centauri, is approximately 4.2 light-years away. Light, which crossed the Earth-Sun distance in 8 minutes, requires more than 4 years to travel from Proxima Centauri to us. That car at highway speed would take roughly 45 million years to make the journey. Between our Sun and Proxima Centauri, there is almost nothing. The interstellar medium, that sparse scattering of atoms and particles we described earlier, fills the space but barely qualifies as matter by any meaningful standard. In practical terms, the space between our Sun and its nearest neighbor is as close to empty as nature offers at stellar scales, and Proxima Centauri is one of our closest neighbors. The Milky Way contains somewhere between 100 billion and 400 billion stars, and the average distance between them is measured in light years. The distances we have been discussing are not exceptional. They are typical. They are what the universe looks like everywhere you care to look. This is the scale of cosmic emptiness, and we are only just beginning to explore its implications. In the chapters ahead, we will look at why matter ended up so thinly distributed, how the large-scale structure of the universe emerged from the early cosmos, and what, if anything, fills the spaces that matter has left behind. But for now, it is enough to sit with the distances themselves, to let the numbers settle, and to appreciate that the universe we inhabit is, by any measure we can devise, overwhelmingly, almost incomprehensibly empty. The room you are in feels solid and full. The ground beneath you feels firm. The air around you feels present and real. All of that is true at the scale at which you exist, but pull back far enough, and what you find is mostly nothing. Understood. Inserting that expansion block now as a seamless addition to Chapter 1, placed right after the final paragraph. But pull back far enough, and what you find is mostly nothing. Another way to appreciate this emptiness is to imagine how little matter would remain if we compressed the universe down to something we could hold in our hands. All of the stars in our galaxy, hundreds of billions of them, contain almost all of the visible matter in the Milky Way. Yet those stars occupy only a tiny fraction of the galaxy's total volume. The vast spaces between them are filled with that extremely thin interstellar medium. a drifting mixture of atoms, ions, and microscopic dust grains so sparse that entire spacecraft can travel through it for years without encountering anything larger than a few stray particles. Even within galaxies, matter gathers only in scattered islands. Stars cluster into galaxies. Galaxies cluster into groups. Groups gather into clusters, and clusters stretch along enormous filaments that form what astronomers call the cosmic web, a vast network of matter extending across hundreds of millions of light years. But between these filaments lie regions known as cosmic voids, enormous volumes of space containing very few galaxies at all. Some of these voids are hundreds of millions of light years across. Inside them, the already sparse matter of intergalactic space becomes even rarer. A galaxy might drift through billions of cubic light years of space before encountering another. From the perspective of the universe as a whole, matter is not evenly distributed. It is concentrated into threads and clusters, leaving most of the cosmic volume almost completely empty. If we could step far enough away to see the entire observable universe at once, the pattern would not resemble a solid structure. It would resemble a delicate web suspended in darkness, with vast hollow regions between the strands. The remarkable thing is that those hollow regions make up the majority of the universe's volume. Chapter 2. The Scale of Space. There is a particular difficulty that comes with trying to understand cosmic distances. Our minds are calibrated for a world of rooms and roads and horizons. We can feel the difference between a meter and a kilometer. We can picture a city, a country, even a planet. But somewhere beyond that, the numbers stop feeling like distances and start feeling like abstractions. They become large in the same way that all large numbers are large, without any real sense of what they mean in practice. It is worth taking some time with this, because the scale of space is not just a backdrop to the story of emptiness. It is the story. Let us build the picture slowly. The solar system, which contains our sun, 8 planets, dozens of moons, and countless smaller bodies, fits within a sphere roughly 2 light years across if we include the outermost reaches of the Oort cloud, the distant shell of icy objects that marks the edge of the sun's gravitational influence. 2 light years. That sounds modest compared to the distances we will discuss shortly, and in galactic terms it is. Our galaxy, the Milky Way, is approximately 100,000 light years in diameter. It contains somewhere between 100 billion and 400 billion stars. If you were to shrink the entire solar system, including that vast Oort cloud, down to the size of a coin, the Milky Way at the same scale would stretch for roughly 2 kilometers. Every star in the galaxy would be another coin, scattered across that 2-kilometer expanse, each one surrounded by its own region of essentially empty space. Even within the Milky Way, the stars are extraordinarily far apart relative to their size. The Sun is roughly 1.4 million kilometers in diameter. If you shrunk the Sun to the size of a marble, roughly 1 centimeter across, the nearest star at that same scale would be approximately 300 kilometers away. Between those 2 marbles, nothing. No planets, no gas clouds of any significance, no structures of any kind. Just space. This is the density of matter inside a galaxy, which is considered one of the denser regions of the universe. It helps to sit with that marble analogy a little longer, because it does something that numbers alone cannot quite accomplish. It gives the emptiness a physical form that the imagination can work with. Imagine standing in a large open field, holding a marble in your hand. That marble is the Sun. Everything in the solar system, the 8 planets, their moons, the asteroid belt, the distant reaches of the Oort cloud, All of it exists within a radius of roughly a few centimeters to a couple of meters from that marble, depending on which part of the system you are considering. The Earth at this scale would be a grain of sand less than a centimeter from the marble. Jupiter would be a small ball, bearing about 5 centimeters away. Now walk 300 kilometers in any direction. That is roughly the distance from one major city to the next in many parts of the world. A journey of several hours by car, a short flight by aircraft. At the end of that journey, place another marble. That is Proxima Centauri, our nearest stellar neighbor. Between your marble and that distant one, nothing. Fields, cities, mountains, coastlines at the human scale, but in terms of the stellar model, complete emptiness. No other marbles, no grains of sand, just the 300-kilometer gap between two lonely spheres of glass. And these two marbles are neighbors. They are among the closest stars in the galaxy. The average separation between stars in the Milky Way is considerably greater than the distance between the Sun and Proxima Centauri. Most of the 300-kilometer gaps in our model would need to be longer, not shorter. Now scale that up to the full galaxy. Hundreds of billions of marbles, each separated from its nearest neighbor by hundreds of kilometers of empty space, all arranged in a disk roughly 100,000 light-years across. The sheer volume of emptiness contained within a single galaxy is already staggering. The matter, all those billions of stars, occupies a tiny fraction of the total volume. The rest is the interstellar medium, that thin scattering of atoms and particles we described in the previous chapter, and beyond even that, simply space. One useful way to appreciate these distances is to remember how small stars actually are compared to the space that surrounds them. Even the Sun, enormous by human standards, is a relatively modest star. If we imagine it expanded until it filled the orbit of the Earth, it would still occupy only a tiny fraction of the space between neighboring stars. Most of the volume of the galaxy is not taken up by stars at all. It is simply the distance between them. In fact, if you could travel through the Milky Way at the speed of light, moving from one star to the next, the overwhelming majority of your journey would not involve passing near stars or planets or gas clouds. It would involve traveling through the dark spaces between them, year after year, decade after decade, with nothing nearby except the occasional drifting particle of interstellar gas. Space, even inside a galaxy, is mostly the distance between things. The stars are the exceptions. Beyond the Milky Way, the distances grow again. The Andromeda Galaxy, our nearest large galactic neighbor, lies approximately 2.5 million light-years away. The light reaching us from Andromeda tonight left its source before our species existed, before Homo sapiens walked the Earth, before the last ice age reshaped our continents, before the oldest stone tools were fashioned by human hands. That light was already traveling toward us across an empty intergalactic void. It has been in transit for longer than our entire evolutionary history as a species. Between the Milky Way and Andromeda, there is almost nothing. A sparse scattering of dwarf galaxies, thin streams of gas, and darkness. The void between galaxies makes the void between stars look crowded by comparison. The Milky Way and Andromeda are both members of a collection of galaxies called the Local Group, which contains roughly 50 galaxies of various sizes spread across a volume approximately 10 million light-years across. Within the Local Group, the galaxies are gravitationally bound to one another, meaning their mutual gravity is strong enough to hold them together against the general expansion of the universe. In about 4 billion years, the Milky Way and Andromeda are expected to collide and eventually merge into a single larger galaxy. Beyond the Local Group, the expansion of the universe carries other galaxy groups and clusters away from us at speeds that increase with distance. The Virgo cluster, the nearest large cluster of galaxies, lies roughly 65 million light-years away. It contains more than 1,000 galaxies. Between us and the Virgo cluster, there are smaller galaxy groups, thin filaments of matter, and large regions of relative emptiness. Further still lies the Laniakea supercluster, the enormous large-scale structure within which the Milky Way resides. Laniakea spans roughly 520 million light-years and contains the mass of 100 million billion suns, gathered across hundreds of thousands of galaxies. It is one of the largest structures in the observable universe. And yet, even Laniakea is dwarfed by the scale of the observable universe itself. The observable universe, the region of space from which light has had time to reach us since the Big Bang, extends roughly 46 billion light-years in every direction from Earth, giving it a diameter of approximately 93 billion light-years. Within that volume, there are an estimated 2 trillion galaxies, each containing hundreds of billions of stars. 2 trillion galaxies sounds like an almost incomprehensibly large number of objects. And yet, when you divide that number by the volume they occupy, what you find is that the average density of matter across the observable universe is extraordinarily low. The galaxies are real and numerous, but the spaces between them are so vast that matter remains a minority feature of the cosmos even at this scale. There is a way of expressing this that is worth considering slowly. If you were to take all the matter in the observable universe and spread it perfectly evenly across the entire volume of space, the average density would work out to roughly 5 or 6 hydrogen atoms per cubic meter. Not per cubic centimeter, per cubic meter. A cube of space 1 meter on each side, spread across the entire observable universe, would contain on average fewer than 10 atoms. This average density is so low that it can be difficult to internalize. 5 atoms per cubic meter means that if you stood inside a cube of space large enough to walk around in, the matter inside that entire volume would amount to only a handful of individual atoms. Not grains of dust, not droplets of gas, but isolated atoms drifting through space with enormous distances between them. At that density, 2 atoms might travel hundreds or thousands of kilometers before encountering one another. Collisions are rare. Interactions are rare. For most of the universe's history, the majority of space has existed in this extremely diffuse state, with matter spread thinly across enormous distances. Gravity slowly gathers some of that matter into stars, galaxies, and clusters, creating the luminous structures we observe with telescopes. But even after billions of years of cosmic evolution, those structures remain islands of concentration in a universe whose dominant characteristic is still emptiness. The galaxies themselves are not the fabric of the cosmos. They are the scattered lights within it. The universe, on average, is almost incomprehensibly empty. What we experience as the material world, the stars, the planets, the oceans, the ground beneath us, exists only because gravity has spent billions of years pulling matter together from that diffuse average into dense, concentrated structures. The richness of the world around us is the result of matter being gathered from an enormous volume of nearly empty space into a very small one. Somewhere out there, in the regions between galaxy clusters, in the great voids that dominate the cosmic landscape, the universe still looks the way it looked on average before gravity had done much of its work. Thin, cold, almost entirely empty, stretching in every direction without end. We are fortunate to be in one of the exceptions. Chapter 3. Why matter is so rare. In the beginning, the universe was not empty at all. In the first fractions of a second after the Big Bang, everything that would eventually become the observable universe was compressed into a region of extraordinary density and temperature. Matter and energy were not yet separate things. Space itself was not yet the quiet, expansive backdrop we described in the previous chapter. It was a seething, uniform plasma, so hot and so dense that the particles we think of as the basic building blocks of matter could not yet hold themselves together. This is worth sitting with for a moment. The universe that exists today, with its vast empty stretches and its isolated pockets of matter, grew from something that was the opposite of empty in almost every way imaginable. So what happened? The short answer is that the universe expanded. And as it expanded, it cooled. And as it cooled, the conditions that had kept matter evenly distributed began to break down, allowing gravity to do something it had not previously been able to do. It began to pull things together. But before we follow that thread, it helps to understand just how little matter the Big Bang actually produced. The universe, for all its billions of galaxies and trillions of stars, is remarkably stingy with matter. Ordinary matter, the kind made of protons, neutrons, and electrons, the kind that makes up stars and planets and everything we have ever touched or seen, accounts for only about 5% of the total energy content of the universe. The remaining 95% is divided between dark matter, which we will explore in a later chapter, and dark energy, the mysterious force driving the accelerating expansion of space. 5%. In a universe that already appears overwhelmingly empty, when we consider only the matter we can detect, that matter itself represents only a small fraction of what exists. Even within that 5%, the distribution is extraordinarily uneven. Most of the ordinary matter in the universe is not contained in stars or planets. It exists as thin, diffuse gas, spread across the vast filaments of the cosmic web and the enormous spaces between galaxies. The stars, for all their number, represent a relatively small portion of the ordinary matter budget. Planets represent an even smaller one. To understand why matter ended up so thinly spread, it helps to think carefully about what the universe looked like in its earliest moments, and what the process of expansion actually means at the deepest level. When physicists say the universe expanded, they do not mean that matter flew outward into a pre-existing empty space, the way debris spreads from an explosion. Space itself expanded. Every point in space moved away from every other point, not because anything was traveling through space, but because the fabric of space itself was stretching. Imagine a grid drawn on a rubber sheet. If you stretch the sheet in all directions, the points on the grid move apart, not because any point is moving across the sheet, but because the sheet itself is growing. The universe works in a similar way, though the geometry involved is considerably more complex. In the earliest moments, this expansion was extraordinarily rapid. In a period known as inflation, thought to have occurred in the first tiny fraction of a second after the Big Bang, the universe is believed to have expanded by an enormous factor in an almost incomprehensibly short time. Regions that had been in contact with each other, close enough to share heat and information, were suddenly separated by distances far too large for light to cross. The theory of inflation was developed in the early 1980s, primarily by the physicist Alan Guth, as a way of explaining several puzzling features of the observable universe. One of those features is the remarkable uniformity of the cosmic microwave background, the faint radiation left over from the early universe. Another is the flatness of the universe's geometry on the larger scales. Inflation provides elegant explanations for both, and while it remains a theoretical framework rather than a directly confirmed fact, it is supported by a substantial body of observational evidence. What matters for our purposes is the consequence of that rapid early expansion. The energy that would eventually become matter was spread across a volume that grew faster than any process could concentrate it. The seeds of the large-scale structure we see today, the filaments and voids and galaxy clusters, were planted during inflation as tiny quantum fluctuations in the density of the early universe were stretched to cosmic scales. After inflation, the universe continued to expand, more slowly but steadily. As it cooled, particles began to form. In the first few minutes after the Big Bang, protons and neutrons assembled from more fundamental particles called quarks, in a process governed by the strong nuclear force. The universe at this stage was still far too hot for atoms to form. Electrons zipped freely through the plasma, constantly interacting with photons of light and preventing them from traveling in straight lines. This hot, opaque plasma persisted for roughly 380,000 years. Then, as the universe continued to cool, something changed. The temperature dropped to the point where electrons could settle into stable orbits around atomic nuclei without immediately being knocked free again by the energetic radiation filling the universe. Atoms formed for the first time, and because neutral atoms interact with light far less than free electrons do, the universe became transparent almost simultaneously across its entire volume. The photons that had been trapped in the plasma were suddenly free to travel. They streamed outward in all directions, carrying with them a snapshot of the universe at that moment. Those photons are still traveling today, cooled by billions of years of cosmic expansion to a temperature just a few degrees above absolute zero. We detect them as the cosmic microwave background, a faint glow of microwave radiation that fills the sky uniformly in every direction. At the moment of that first transparency, the universe was still remarkably uniform. The matter that existed was spread almost evenly across space, with only tiny variations in density from one region to the next. Those variations, small as they were, would turn out to be enormously important. They were the seeds of everything that followed. Those tiny variations in density were extraordinarily small. Measurements of the cosmic microwave background show that the differences from one region to another were only about 1 part in 100,000. If you could map the density of matter in the early universe with perfect precision, the entire observable cosmos would appear almost perfectly smooth, with only the faintest ripples breaking that uniformity. And yet, those ripples were enough. Gravity does not require large differences to begin its work. Even the slightest excess of matter in one region creates a slightly stronger gravitational pull. That stronger pull attracts a little more matter from the surrounding space. As that matter arrives, the gravitational pull becomes stronger still. The process feeds on itself. Over time, the tiny ripples grow into larger structures. Regions that were only marginally denser than their surroundings begin to accumulate gas and dark matter. Regions that were slightly less dense gradually lose matter as it flows away toward the growing concentrations nearby. This slow redistribution of matter transforms the smooth early universe into something far more complex. Gravity is patient. It does not need to hurry. Over millions and then hundreds of millions of years, the slightly denser regions of the early universe began to attract more matter from their surroundings. The process was slow at first, almost imperceptible on human timescales, but it was relentless. Denser regions became denser still. The matter between them thinned out as it was drawn toward the growing concentrations. The first stars ignited somewhere between 100 million and 200 million years after the Big Bang, in regions where gas had condensed enough to trigger nuclear fusion. These early stars were very different from the Sun. They were massive, hot and short-lived, burning through their fuel in millions rather than billions of years before exploding as supernovae and seeding the surrounding space with the heavier elements they had forged in their cores. Galaxies began to form around concentrations of dark matter that had been accumulating since before the first atoms existed. The dark matter halos provided gravitational wells into which ordinary matter fell, cooling and condensing into the rotating disks and elliptical structures we recognize as galaxies today. Clusters of galaxies assembled along filaments of matter stretching across millions of light years. And as matter gathered into these structures, the spaces between them became emptier. The matter that collected into galaxies and clusters left the voids between them increasingly bare. This is the process that produced the universe we observe today. Not a uniform distribution of matter thinning gradually with distance, but a highly structured arrangement of dense concentrations separated by vast emptinesses. The cosmic web, with its filaments and nodes and voids, is the direct product of gravity acting over billions of years on the tiny density variations seeded by inflation. If we could watch this process unfold over cosmic time, the universe would not appear chaotic or explosive. Instead, it would resemble a slow and graceful rearrangement. Matter would drift along invisible gravitational pathways, flowing toward regions of slightly higher density. Filaments of gas and dark matter would gradually thicken as more material joined them. At the intersections of those filaments, galaxies would begin to form, first as faint clouds of gas, then as clusters of newborn stars. Meanwhile, the regions between these structures would slowly empty. Matter that once occupied those spaces would migrate toward the filaments and nodes of the cosmic web. Over billions of years, the contrast between dense regions and empty regions would grow sharper. The galaxies would shine more brightly, while the voids between them would become darker and quieter. The universe would begin to resemble a vast network of luminous islands connected by delicate threads suspended within enormous volumes of nearly perfect emptiness. This is the pattern astronomers observe today when they map the distribution of galaxies across hundreds of millions of light years. It is a structure shaped not by sudden violence but by patience. Gravity works slowly, but given enough time, even the smallest imbalance can transform the entire architecture of the cosmos. Emptiness, in a sense, is a byproduct of structure. The universe did not start empty and gradually fill in. It started relatively uniform and became emptier in most places as matter concentrated in others. Every galaxy that formed, every star that ignited, every planet that coalesced from a disk of gas and dust, made the surrounding universe a little emptier by drawing matter toward itself. The emptiness we observe today is the shadow of all the structure that has formed. The voids grew as the filaments thickened. The dark spaces between galaxies deepened as the galaxies themselves brightened. There is something quietly elegant about this. The same process that created the stars also created the darkness between them. The same gravity that gathered matter into the complex structures that eventually gave rise to life also emptied the vast majority of cosmic space of nearly everything. The universe is not empty despite having structure. It is empty because of it. And the story of that emptiness does not end at the scale of galaxies and clusters. There is another dimension to explore, one that operates not in the vast spaces between stars, but in the infinitesimally small spaces within the matter itself. Chapter 4. Empty at the smallest scale. We have been thinking about emptiness at the largest scales the universe offers. Distances between stars measured in light years. Voids between galaxy clusters spanning hundreds of millions of light years. The thin distribution of matter across a universe that is mostly nothing. But there is another way to approach the question of emptiness, and it leads somewhere unexpected. If we turn our attention not outward to the cosmos, but inward to the structure of matter itself, we find that the emptiness does not stop at the space between galaxies. It goes all the way down. Everything you have ever touched is mostly empty space. This is one of those statements that is easy to read and difficult to genuinely absorb. The chair you are sitting in, the ground beneath your feet, the body you inhabit, all of it is composed of atoms, and atoms are almost entirely empty. Let us build that picture carefully. An atom consists of a nucleus at its center, surrounded by electrons. The nucleus contains protons and neutrons, bound tightly together, and accounts for nearly all of the atom's mass. The electrons occupy a region around the nucleus that is vast by comparison, a cloud of probability rather than a solid shell, spread across a volume that dwarfs the nucleus many thousands of times over. If you were to scale a hydrogen atom up so that its nucleus was the size of a marble, roughly 1 centimeter across, the electron's region of influence would extend to a distance of approximately 1 kilometer from that marble. Everything between the marble and that outer boundary would be empty, not filled with air, not filled with anything detectable, simply space. The nucleus itself, which contains virtually all of the atom's mass, occupies an almost inconceivably small fraction of the atom's total volume. The rest is nothing. And atoms, of course, are the building blocks of everything. Every solid surface, every liquid, every gas, every living thing is made of structures that are overwhelmingly empty at their core. The solidity we experience when we press our hand against a table is not the result of matter being packed tightly together. It is the result of electromagnetic forces, the repulsion between the electron clouds of adjacent atoms, pushing back against the pressure we apply. You have never actually touched anything. What you experience as touch is the electromagnetic interaction between the atoms of your fingertips and the atoms of whatever you are touching. The matter itself never makes contact. This is a strange thing to consider on a quiet evening. The world feels so solid, so present, so full, and yet the substance of it, the actual matter, occupies only a tiny fraction of the space it appears to fill. To appreciate just how empty an atom really is, it helps to follow the numbers carefully. The nucleus of a hydrogen atom, a single proton, has a diameter of roughly 1 femtometer, which is 1/millionth of a billionth of a meter. The electron cloud surrounding that nucleus extends to a radius of roughly 53 picometers, which is about 53 trillionths of a meter. The ratio of the electron cloud's radius to the nucleus's radius is approximately 50,000 to 1. This means that if the nucleus was scaled up to 1 centimeter, the atom itself would be 500 meters across, a sphere half a kilometer in diameter, with a marble at its center and nothing else inside it. That is a hydrogen atom. It can be difficult to imagine such a structure because our everyday experience offers no direct comparison. In the world we inhabit, empty space rarely exists on such dramatic scales. A room may feel empty when the furniture is removed, but the air still fills every corner. Even the best laboratory vacuums contain trillions of particles drifting through them. An atom, by contrast, contains a kind of emptiness far more profound. If you were somehow able to shrink yourself down to atomic scale and explore this enlarged hydrogen atom, the nucleus at its center would appear as a dense, compact object, but the surrounding region would look almost completely vacant. There would be no orbiting particles tracing neat circular paths the way early textbook illustrations suggested. Instead, the electron would exist as a diffuse cloud of probability, a region where it might be found if measured. Most of the time, you would encounter nothing at all. You could travel vast distances across that kilometer-wide atomic landscape without encountering a single particle. The atom would feel less like a miniature solar system and more like a tiny universe. Heavier atoms are somewhat more complex, with multiple protons and neutrons in the nucleus and multiple electrons in various orbital shells around it. But the basic proportions hold. The nucleus remains a tiny, dense point at the center of a vast, mostly empty volume, occupied only by the diffuse probability clouds of orbiting electrons. Now consider what this means at the scale of ordinary objects. A single grain of table salt contains roughly 1.2 quintillion atoms, arranged in a regular crystal lattice. Each of those atoms is mostly empty space. The lattice structure holds them at fixed distances from one another, with the electron clouds of adjacent atoms interacting through electromagnetic forces to maintain the crystal's shape and solidity. What feels like a solid object to your fingers is, at the atomic scale, an arrangement of widely spaced nuclei surrounded by electron clouds, with enormous empty volumes between them and within them. The apparent solidity is entirely a product of the electromagnetic forces that govern how those electron clouds interact. The same is true of every object you have ever handled. Your own body, the ground you are lying on, the air you are breathing, all of it follows the same pattern. Matter that appears continuous and solid at human scales is, at atomic scales, almost entirely empty, with tiny, dense nuclei scattered through vast volumes of near-nothingness. There is a calculation worth considering here. If you were to somehow compress all the matter in a human body, removing all the empty space between atoms and all the empty space within atoms, packing only the actual subatomic particles together as tightly as physically possible, the result would be extraordinarily small. Estimates vary depending on the assumptions made, but the compressed matter of a human body would fit within a volume roughly the size of a speck of dust. All the atoms, all the nuclei, all the protons and neutrons compressed to nuclear density would occupy a space far smaller than anything visible to the naked eye. The rest of you is empty. This is not merely a curiosity. It connects to some of the deepest questions in physics about why matter behaves the way it does, why it feels solid when it is mostly nothing, and what the fundamental nature of physical reality actually is. The answer to the first question, why matter feels solid despite being mostly empty, lies in the behavior of electrons and the electromagnetic force. When two objects are pressed together, their electron clouds begin to overlap. The Pauli exclusion principle, a fundamental rule of quantum mechanics, states that no two electrons can occupy the same quantum state simultaneously. As the electron clouds of adjacent atoms approach each other, this principle creates a powerful repulsive force that resists further compression. It is not the matter itself that makes objects feel solid. It is the electromagnetic and quantum mechanical forces that govern how matter behaves. This insight has a subtle but important implication. The properties we associate with matter, its solidity, its impenetrability, its resistance to compression, are not intrinsic properties of the matter itself. They are emergent properties that arise from the interactions between particles that are themselves mostly empty space, governed by forces that operate across the emptiness between them. Solidity is, in a sense, an illusion, not in the philosophical sense that it does not exist, but in the physical sense that it is not what it appears to be. What we call solid is really a set of force relationships operating across near emptiness. This realization marked one of the most profound shifts in our understanding of matter during the early 20th century. For centuries, matter had been imagined as a continuous substance, something that filled space in a solid and tangible way. The development of atomic physics and quantum mechanics revealed that the true structure of matter was far stranger. Particles were not tiny billiard balls packed tightly together. They were localized concentrations of energy existing within fields that extend through space. Their positions were not fixed points, but probabilities, governed by mathematical descriptions that predict where they are most likely to appear. The solidity of the world around us emerges from these invisible interactions. When you press your hand against a table, trillions upon trillions of electrons interact through electromagnetic forces. Those forces resist compression so effectively that the table feels perfectly rigid. Yet between those particles and within them, enormous regions of space remain empty. In a sense, the universe has built its most complex structures not by filling space with matter, but by arranging small amounts of matter within vast frameworks of emptiness. Now consider what this means for the universe as a whole. We have already established that matter is extraordinarily thinly distributed across cosmic scales. Galaxies separated by millions of light years, stars separated by light years within those galaxies. And now we find that the matter itself, when you examine it closely, is almost entirely empty at the atomic scale. If you were to somehow compress all the matter in the observable universe, removing all the empty space between atoms and all the empty space within atoms, packing only the actual subatomic particles together as tightly as physically possible, the result would fit within a sphere far smaller than you might expect. Some estimates suggest that all the matter in the observable universe, compressed to nuclear density, would fit within a sphere roughly the size of a large star. Others suggest something considerably smaller, depending on the assumptions made about the total matter content. The precise figure is less important than the principle. The universe contains an almost incomprehensible amount of space and a comparatively tiny amount of actual matter, and even that matter is itself mostly space. Going deeper still, even the protons and neutrons within atomic nuclei are not solid objects. They are composed of quarks, held together by the strong nuclear force through the exchange of particles called gluons. The quarks themselves are currently understood to be fundamental particles with no internal structure, point-like objects with no measurable size, and the space within a proton, between its quarks, is filled not with matter, but with the energy of the gluon fields that bind them. At every scale we examine, from the largest structures in the observable universe down to the smallest constituents of matter, the same pattern repeats. Tiny concentrations of something surrounded by vast expanses of near nothing. Structure emerging from emptiness, held together by forces that operate across the void. The universe is empty at every scale we can measure. The question that follows naturally from this is whether any of that emptiness is truly, completely, absolutely empty. Whether there exists anywhere in the cosmos a region of space that contains nothing at all. The answer, as we are about to discover, is stranger than the question. Chapter 5. Cosmic Voids. We have been moving through layers of emptiness, from the spaces between stars to the distances between galaxies, to the emptiness inside matter itself. Now we arrive at the largest empty structures the universe contains. Regions of space so vast and so bare that even the word empty begins to feel inadequate. These are the cosmic voids. A cosmic void is not simply a region where stars are scarce. It is a region where galaxies themselves are scarce or absent altogether, where the large-scale structure of the universe, the filaments and walls and clusters we described in earlier chapters, simply does not exist, where space extends for hundreds of millions of light years in every direction and contains, as far as our instruments can detect, almost nothing at all. To understand how voids fit into the broader picture, it helps to think about the large-scale structure of the universe as a whole. If you could step back far enough to see the observable universe in its entirety, what you would find is not a uniform distribution of galaxies scattered evenly across space. What you would find looks something like a vast, three-dimensional web. Galaxies and galaxy clusters are concentrated along thin filaments, like beads on a string. Where filaments intersect, enormous superclusters gather. And between the filaments, occupying the majority of the universe's total volume, are the voids. This structure, which cosmologists call the cosmic web, emerged from the same tiny variations in density that we discussed in the previous chapter. The regions that were slightly denser than average in the early universe attracted more matter over time, eventually forming the filaments and clusters we see today. The regions that were slightly less dense lost matter to their denser neighbors, growing emptier as the universe aged. The process was not instantaneous. It unfolded over billions of years, slowly and without drama. Matter drifted along invisible, gravitational pathways, accumulating along the filaments and draining away from the regions between them. The voids did not form suddenly. They deepened gradually, like shallow depressions in a landscape that slowly erode into valleys as the surrounding terrain is shaped by time. Today, those valleys are vast. Cosmologists classify voids by their size and by the degree to which they are underdense compared to the cosmic average. Small voids might span only a few tens of millions of light years. Medium voids range from roughly 100 to 300 million light years across. And then there are the supervoids, structures so large that they strain the imagination and, when they were first discovered, strained the theoretical models cosmologists used to describe the universe. Before we arrive at the largest known examples, it is worth spending a moment with what it would actually feel like to be inside a void. Imagine being transported to a point deep inside a typical cosmic void. You would be floating in space, except that the view in every direction would be dramatically different from anything visible from within the Milky Way. From our position inside a galaxy, the night sky is full of stars. The Milky Way itself stretches across the sky as a band of light. Distant galaxies are visible with telescopes in every direction. From inside a void, the sky would be almost completely dark. The nearest galaxies would be hundreds of millions of light years away in every direction. The night sky, even with the most powerful telescope imaginable, would show only a handful of extremely distant, faint objects. The sense of isolation would be absolute. You would be surrounded by hundreds of millions of light years of near emptiness in every direction, with a faint glow of the cosmic web visible only at the very edges of your observational range. It is a landscape with no human analogy. Not a desert, not an ocean, not the open sky. Something qualitatively different, a silence and a distance that have no equivalent in any environment our species has ever inhabited. The voids are not static, they are growing. As the universe continues to expand, and as dark energy accelerates that expansion, the voids are becoming larger and emptier over time. Matter continues to drain away from them along the gravitational gradients that connect them to the surrounding filaments, leaving the interiors increasingly bare. In the very long run, as dark energy comes to dominate the universe's behavior more completely. The voids will continue to grow until even the filaments begin to dissolve, leaving an increasingly uniform and empty cosmos. But that future is far away. For now, the voids are simply the dominant landscape of the present universe. Some voids are relatively modest in scale, spanning tens of millions of light years. Others are considerably larger. And then there are structures like the Bootes void. The Bootes void was discovered in 1981 by astronomer Robert Kirshner and his colleagues, who were surveying the distribution of galaxies in a region of the sky in the direction of the constellation Bootes. What they found was unexpected. A roughly spherical region of space, approximately 330 million light-years in diameter, containing almost no galaxies at all. To appreciate the scale of this, consider that the entire distance between the Milky Way and the Andromeda Galaxy, 2.5 million light-years, could fit inside the Bootes void more than 100 times over. The void is so large that when astronomers first measured it, some were skeptical of the result. Structures of that size were not predicted by the cosmological models of the time, and the discovery prompted significant debate about whether our understanding of how the universe formed was missing something important. Subsequent surveys have confirmed the void's existence and refined its boundaries. It is real, and it is genuinely enormous. Within its interior, a small number of galaxies have been found, roughly 60, but given the volume of space involved, this represents a density far below the cosmic average. For practical purposes, the Bootes void is as close to true emptiness as the universe offers on large scales. The question of how the Bootes void formed is still not completely resolved. Current cosmological models can produce voids of that general size, though they are rare in simulations, arising from the chance superposition of several smaller voids that have merged over time into a single larger structure. The Bootes void may represent an unusually extreme outcome of the same void formation process that operates everywhere, a region where the ordinary emptying of space happened to proceed further and faster than typical. The Bootes void is the most famous of the cosmic voids, but it is not the largest structure of its kind that astronomers have identified. In 2004, astronomers using data from the Sloan Digital Sky Survey identified a structure known as the Sloan Great Wall, a filament of galaxies stretching roughly 1.4 billion light-years across. On the other side of such enormous structures lie corresponding voids of comparable scale. More recently, surveys have identified supervoid structures spanning over 1 billion light-years, regions of significantly below average density that may leave subtle imprints on the cosmic microwave background as photons pass through them. One such feature, sometimes called the cold spot, is a region of the cosmic microwave background that is slightly cooler than its surroundings. One proposed explanation is that it corresponds to a supervoid along the line of sight, through which photons lose a small amount of energy as they travel. The existence and origin of the cold spot remains an active area of research, and the supervoid explanation is one of several that have been proposed. Astronomers did not discover cosmic voids all at once. For much of the 20th century, the distribution of galaxies was known only in small patches of the sky. Individual galaxies and clusters could be identified, but the overall architecture of the universe remained unclear. That began to change as larger and more detailed surveys were conducted. In the late 20th century, astronomers began measuring the distances to thousands and eventually millions of galaxies. When these measurements were plotted in 3 dimensions, the pattern that emerged surprised many researchers. Instead of filling space uniformly, galaxies traced out long, thin structures. These structures formed walls and filaments that curved across enormous distances. Between them lay large regions where very few galaxies appeared at all. As the surveys grew larger, those empty regions became more obvious. The universe was not evenly filled with galaxies. It had structure. Some of the earliest visualizations of this structure resembled slices through a giant loaf of bread. Galaxies appeared along the crusts and ridges, while the interior regions were mostly empty. Later maps revealed the pattern more clearly, showing the cosmic web in 3 dimensions. The voids were not isolated holes scattered randomly through space. They were interconnected. Smaller voids merged with neighboring voids as matter flowed toward the surrounding filaments. Over time, these merging regions created larger and larger empty volumes, producing the vast cosmic bubbles astronomers observe today. Modern galaxy surveys, including projects such as the Sloan Digital Sky Survey and the Dark Energy Survey, have mapped millions of galaxies across enormous regions of space. These maps reveal hundreds of cosmic voids, each one a region where matter is significantly less dense than the cosmic average. Together, these voids form the majority of the universe's volume. What we see as the grand architecture of the cosmos, the galaxies, clusters, and superclusters, is actually the thin framework surrounding these immense empty regions. There is something worth pausing on here. When we look up at the night sky, what we see gives an impression of a universe that is populated, if sparsely. But that impression is shaped entirely by where we happen to be standing. We are inside a galaxy, which is part of a galaxy cluster, which sits along a filament of the cosmic web. We are, by cosmic standards, in one of the more crowded regions of the universe. If you were instead located inside the Bootes void, the night sky would look very different. The nearest galaxies would be hundreds of millions of light years away in every direction. The sky would be darker, the universe around you more silent, the sense of isolation more complete than anything we can experience from our position inside the Milky Way. Our view of the universe is, in a sense, a privileged one. We observe from within one of the structures that gravity has built, surrounded by the light of hundreds of billions of nearby stars, within reach of the glow of thousands of neighboring galaxies. This is not the typical vantage point for an observer in the universe. The typical vantage point, if we could call it that, would be somewhere in a void, surrounded by hundreds of millions of light years of near emptiness, with the faint outlines of distant filaments barely visible at the edge of observational range. The universe is not a place of lights with darkness between them. It is a place of darkness with lights at the edges. The voids are not merely gaps in the map. They are the dominant landscape of the cosmos, the default condition of space, the setting within which the rare and improbable structures of galaxies and stars exist as temporary exceptions. And they raise a quiet but persistent question. If the universe is mostly void, and if even the matter within it is mostly empty space, what exactly fills all that emptiness? The answer, as we are about to see, is stranger than the emptiness itself. Chapter 6: Dark Matter and the Invisible Structure. We have spent several chapters looking at emptiness from the outside, measuring the distances between things, cataloguing the voids, and appreciating just how little ordinary matter the universe contains. Now we need to complicate the picture somewhat, because the emptiness is not as empty as it looks. When astronomers map the distribution of galaxies across the universe, what they are actually mapping is light. The galaxies they can see are the ones that emit or reflect radiation detectable by their instruments. But there is considerable evidence, accumulated over decades of observation and refined by increasingly sophisticated measurements, that the matter we can see represents only a fraction of the matter that actually exists. The rest is dark matter. Dark matter does not emit light. It does not reflect light. It does not interact with electromagnetic radiation in any way that our instruments can currently detect directly. Its existence is inferred entirely from its gravitational effects on the things we can see. The evidence for dark matter is both extensive and varied, and it is worth taking some time to appreciate how that evidence was built up, because it represents one of the most compelling examples in the history of science of a conclusion reached not through direct observation, but through the careful accumulation of indirect evidence pointing consistently in the same direction. The first serious indication that something was missing from our accounting of the universe came from the Swiss astronomer Fritz Zwicky in the 1930s. Zwicky was studying the Coma cluster, a large collection of galaxies roughly 320 million light-years from Earth. By measuring the velocities of individual galaxies within the cluster, he was able to estimate how much gravitational force would be needed to keep the cluster bound together, rather than flying apart. When he compared that estimate to the mass he could calculate from the visible light the galaxies emitted, the numbers did not match. The cluster appeared to contain far more gravitational influence than its visible matter could account for. Zwicky called the missing component dunkle Materie, dark matter. His findings were noted, but not widely pursued at the time. The tools and data available to astronomers in the 1930s were limited, and the discrepancy Zwicky identified, though real, was difficult to follow up on with the technology of the era. It would be decades before the full significance of his observation became clear. In the intervening years, other astronomers noticed similar discrepancies in other systems. The masses of individual galaxies, estimated from their luminosity, did not always match the masses implied by their gravitational influence on neighboring objects. Clusters of galaxies seemed to contain more mass than could be accounted for by their visible stars and gas. The pattern was consistent, appearing in system after system, at scale after scale, but without a clear theoretical framework to explain it. The observations remained puzzling rather than conclusive. That began to change in the 1960s and 1970s, when increasingly precise instruments made it possible to measure the rotation of individual galaxies in detail. Vera Rubin was studying the rotation of spiral galaxies, measuring how far stars at different distances from the galactic center were moving in their orbits. According to standard gravitational physics, stars at the outer edges of a galaxy should move more slowly than stars closer to the center, in the same way that the outer planets of our solar system move more slowly in their orbits than the inner ones. This is because most of the mass of the solar system is concentrated at the center, in the Sun, and gravity weakens with distance. But that is not what Rubin found. The stars at the outer edges of galaxies were moving at roughly the same speed as the stars closer in, and in some cases faster. The rotation curves of galaxies were flat, where they should have been declining. Rubin did not arrive at this finding quickly or easily. She spent years carefully measuring the rotation of galaxy after galaxy, building up a dataset that was difficult to dismiss. Her work, conducted alongside her colleague Kent Ford, whose expertise in instrumentation made the precise measurements possible, produced results that were initially met with skepticism by parts of the astronomical community. The implications were significant enough that some researchers looked for alternative explanations before accepting that something genuinely unexpected was going on. The most straightforward explanation was that the visible matter in galaxies represents only a portion of the total mass. If galaxies are embedded in vast halos of invisible matter extending far beyond their visible boundaries, the additional gravitational influence of that halo could explain the flat rotation curves. The outer stars are not moving too fast for their galaxy. They are moving at the speed appropriate for the total mass they are embedded in, most of which we cannot see. Rubin's work, along with Zwicky's earlier observations and a growing body of supporting evidence from other directions, established dark matter as a serious scientific concept rather than a speculative one. Today, it occupies a central place in our standard model of cosmology. Since Rubin's work, evidence for dark matter has continued to accumulate from multiple independent directions, each one strengthening the case further. One of the most visually striking pieces of evidence comes from gravitational lensing. Einstein's general theory of relativity predicts that massive objects bend the path of light passing near them, in the same way that a lens bends the path of light passing through glass. This effect has been confirmed many times over, and it provides a way to measure the total mass of an object, including any invisible component, by observing how much it bends the light of background objects behind it. When astronomers apply gravitational lensing measurements to galaxy clusters, they consistently find that the total mass implied by the lensing is far greater than the mass visible in stars and gas. The invisible component, distributed in a halo around and through the cluster, is precisely what dark matter models predict. The lensing measurements and the rotation curve measurements, conducted using entirely different techniques and entirely different datasets, point to the same conclusion. Another piece of evidence comes from the cosmic microwave background. The detailed pattern of temperature variations in this ancient radiation carries information about the conditions in the early universe, including the relative amounts of ordinary matter, dark matter, and dark energy. Fitting theoretical models to the observed pattern produces estimates of the dark matter content of the universe that are consistent with those derived from rotation curves and gravitational lensing. Three independent lines of evidence converging on the same answer. Perhaps the most dramatic single piece of evidence comes from a system known as the bullet cluster. The bullet cluster is actually two galaxy clusters that collided with each other roughly 150 million years ago. When galaxy clusters collide, the ordinary matter in them, primarily hot gas, interacts electromagnetically and slows down, piling up in the region between the two clusters. But the dark matter, which does not interact electromagnetically, passes through the collision largely unaffected, continuing onward with the galaxies themselves. Observations of the bullet cluster using both X-ray telescopes, which detect the hot gas, and gravitational lensing maps, which reveal the total mass distribution, show exactly this pattern. The hot gas is concentrated in the middle of the collision zone. The mass, as revealed by lensing, is concentrated in two separate clumps that have passed through each other and continued moving apart. The separation between where the mass is and where the ordinary matter is provides some of the most direct evidence that dark matter exists as a distinct component, separate from the ordinary matter we can see. It is worth pausing on what the bullet cluster observation actually means. In most situations, dark matter and ordinary matter occupy the same regions of space. Galaxies sit inside dark matter halos. Galaxy clusters are permeated by both hot gas and dark matter. The two components are mixed together, making it difficult to separate their individual contributions by observation alone. The collision that created the bullet cluster provided a rare opportunity. The collision separated the dark matter from the ordinary matter, spreading them into distinct regions of space and allowing astronomers to map each component independently. The result was a kind of before and after picture. Before the collision, both components occupied the same region. During and after the collision, they separated, with the ordinary matter slowing and the dark matter continuing. The lensing maps show mass concentrated where no visible matter exists. That offset between visible matter and total mass is difficult to explain without invoking a component that does not interact electromagnetically. Dark matter fits that requirement precisely. The current best estimate is that dark matter constitutes approximately 27% of the total energy content of the universe, compared to 5% for ordinary matter. It is more than 5 times as abundant as the matter we can see, and its distribution shapes the large-scale structure of everything. What dark matter actually is remains one of the most important open questions in physics. Numerous candidates have been proposed over the decades. Weakly interacting massive particles, known as WIMPs, were for a long time considered the most promising candidates. They would be particles with mass comparable to or greater than a proton, interacting with ordinary matter only through gravity and the weak nuclear force. Extensive searches for WIMPs, using underground detectors designed to catch the rare occasions when a WIMP might interact with an ordinary atomic nucleus, have so far not produced a confirmed detection. Those underground detectors are remarkable instruments in their own right. They are placed deep below the surface to shield them from the constant rain of cosmic rays that would otherwise overwhelm the signal. They are built from materials chosen for their extraordinary purity, because even trace amounts of radioactive contamination would produce false signals. They operate continuously, monitoring volumes of detector material for the faint signatures that a single dark matter interaction might leave behind, and they have found nothing definitive. This absence of detection does not mean dark matter does not exist. It means that if WIMPs are dark matter, they interact even more weakly with ordinary matter than the simplest models predicted. The searches continue, with each new generation of a detector more sensitive than the last. Other candidates include axions, hypothetical particles originally proposed to solve a different problem in particle physics entirely, and sterile neutrinos, a heavier cousin of the neutrinos we already know exist. More exotic proposals include primordial black holes. Black holes formed in the early universe before stars existed, which could in principle account for some or all of the dark matter if they exist in sufficient numbers and with the right mass distribution. Each of these candidates has motivated its own dedicated search program, and each search has so far returned the same result: no confirmed detection. Dark matter remains detected only through its gravitational influence, its identity unknown. This is a remarkable situation. We know dark matter exists with considerable confidence. We know roughly how much of it there is. We know how it is distributed on large scales. We know that it played a crucial role in the formation of galaxies and the cosmic web. And yet, we do not know what it is made of, whether it is a single type of particle or several, whether it has any interactions beyond gravity, or whether our current theoretical frameworks are adequate to describe it. There is something humbling about this. The universe's dominant form of matter, the substance that provided the gravitational scaffolding for every galaxy that has ever formed, remains beyond our ability to directly detect or identify. We have mapped its distribution across billions of light years. We have measured its influence on the rotation of galaxies and the bending of light. We have constrained its properties through multiple independent observations, and still it eludes us. The cosmic web we described in the previous chapter, the filaments and clusters along which galaxies are concentrated, is not primarily a structure of ordinary matter. It is a structure of dark matter, with ordinary matter gathered along the gravitational scaffolding that dark matter provides. The voids are not simply regions where galaxies are absent. They are regions where dark matter is also relatively sparse, though not entirely absent. When we look at the large-scale structure of the universe and see the luminous filaments of galaxies tracing the cosmic web, we are seeing only the visible surface of a much deeper structure. The dark matter halos that surround every galaxy, the dark matter filaments that connect galaxy clusters across hundreds of millions of light years, the diffuse dark matter that fills even the voids to some degree. All of this is invisible to conventional telescopes. It is present everywhere, shaping everything, detectable only through the gentle curvature it imprints on the paths of light and the orbits of stars. This changes the picture of cosmic emptiness in an important way. The voids are emptier of ordinary matter than they are of everything. The spaces between galaxies, which appear barren when observed with instruments sensitive only to light, are threaded with the invisible scaffolding of dark matter. Even the most remote regions of a cosmic void are not entirely empty. They contain something, even if that something remains beyond the reach of direct detection. Dark matter fills the universe in ways we can measure but not see, shapes structures we can map but not fully explain, and constitutes a majority of the matter content of the cosmos, while remaining one of the deepest mysteries in all of science. And dark matter is not the only thing filling the apparent emptiness. There is something else present in the spaces between galaxies, between stars, between the atoms of every object that has ever existed. Something that physics has only begun to characterize in the past century, and which turns out to be one of the most surprising features of the universe. Empty space, it turns out, is not actually empty, not even close. Chapter 7. The Quantum Vacuum. We have arrived at one of the most quietly remarkable ideas in all of physics. Throughout this exploration, we have been building a picture of a universe defined by emptiness, vast distances between stars, enormous voids between galaxy clusters, atoms that are themselves mostly space, a cosmos in which matter is the exception and absence is the rule. It would be natural to assume that the logical endpoint of all this is a kind of ultimate emptiness, a true void, a region of space containing absolutely nothing at all. But physics does not cooperate with that assumption. When physicists examine empty space carefully, what they find is not nothing. What they find is something far stranger. A vacuum, in the quantum mechanical sense, is not an absence of everything. It is a seething, fluctuating medium, filled with activity at scales so small that they have no counterpart in ordinary experience. To understand why, we need to spend some time with one of the central principles of quantum mechanics, a principle so counterintuitive that even its discoverer found it difficult to accept at first. The Heisenberg uncertainty principle, formulated by the German physicist Werner Heisenberg in 1927, states that certain pairs of physical properties cannot both be known with arbitrary precision at the same time. The more precisely you know the position of a particle, the less precisely you can know its momentum, and vice versa. This is not a limitation of our measuring instruments. It is not a consequence of the act of measurement disturbing the thing being measured, though that is a common misconception. It is a fundamental feature of the way the universe works at small scales. Particles do not have perfectly defined positions and momenta simultaneously. The uncertainty is built into the fabric of physical reality. This principle did not emerge from nowhere. It arose from the strange behavior of matter and energy at quantum scales, behavior that had been accumulating in experimental results for decades before Heisenberg gave it a precise mathematical form. the photoelectric effect, the discrete energy levels of atoms, the interference patterns produced by single particles, all of these phenomena pointed toward a world in which the classical concepts of position, momentum, and energy needed to be replaced by something more subtle and more probabilistic. Heisenberg's uncertainty principle was part of the theoretical framework that made sense of those observations. It described, in precise mathematical terms, the fundamental limits on what can be known about a quantum system. A related form of the uncertainty principle applies to energy and time. The more precisely you try to define the energy of a system over a very short time interval, the more uncertain that energy becomes. And this has a remarkable consequence for empty space. If you take a region of space and remove everything from it, you might expect its energy to be precisely zero. But the uncertainty principle does not allow this. A precisely zero energy maintained over any period of time would violate the relationship between energy and time uncertainty. Instead, even in a perfect vacuum, energy fluctuates. The vacuum is not a state of zero energy. It is a state of minimum energy, and that minimum is not zero. This minimum energy of the vacuum is called the zero-point energy, and its existence has measurable consequences. The most immediate consequence is the existence of what physicists call virtual particles. In the quantum vacuum, pairs of particles and antiparticles spontaneously appear out of the fluctuating energy of empty space, exist for an extraordinarily brief moment, and then annihilate each other and disappear again. The word virtual is used to distinguish these fleeting pairs from real particles, which persist and can be directly detected. But virtual particles are not imaginary or merely mathematical conveniences. They have real, measurable effects on the physical world. To understand this more concretely, it helps to think about what quantum field theory actually says about the nature of space. In the framework of quantum field theory, the most successful theoretical description of the subatomic world that physics has so far produced, the fundamental constituents of reality are not particles but fields. A field, in the physical sense, is a quantity that has a value at every point in space. The electromagnetic field, for instance, has a value at every location in the universe, and disturbances in that field propagate as electromagnetic waves, including light. Electrons are disturbances in the electron field. Photons are disturbances in the electromagnetic field. Every type of particle corresponds to a type of field that permeates all of space. And here is the crucial point. Those fields cannot be completely still. The uncertainty principle forbids it. A field with a precisely defined value of zero everywhere would violate the energy-time uncertainty relation. Instead, every quantum field fluctuates constantly, even in its lowest energy state, even in a region of space that is as empty as it can possibly be made. The vacuum, in quantum field theory, is not empty space. It is the lowest energy state of all the fields that exist, and that state is one of ceaseless, imperceptible activity. These vacuum fluctuations are not merely theoretical. They produce observable effects that have been measured with great precision. The Casimir effect, first predicted in 1948 by the Dutch physicist Hendrik Casimir, and later confirmed experimentally, is one of the most striking demonstrations of vacuum energy in action. If you place two uncharged, perfectly conducting metal plates very close together in a vacuum, with no electric charge and no external force acting on them, they experience a small but measurable attractive force pulling them toward each other. This force has no classical explanation. The plates are uncharged. There is nothing between them. And yet they attract. The quantum mechanical explanation is elegant. The vacuum fluctuations that fill all of space include fluctuations at every possible wavelength. But between the two plates, only fluctuations whose wavelengths fit an integer number of times into the gap between the plates are permitted. The plates act as a boundary condition that restricts which vacuum fluctuations can exist in the space between them. Outside the plates, all wavelengths are permitted. Inside, only a subset are allowed. This asymmetry creates a difference in the energy density of the vacuum between the plates and outside them. The region between the plates has slightly less vacuum energy than the region outside, and that difference in energy density produces a real physical force pushing the plates together. The Casimir effect has been measured experimentally with considerable precision. The measured force matches the theoretical prediction to within the accuracy of the best available experiments. Empty space pushes metal plates together because empty space is not truly empty. Another measurable consequence of vacuum fluctuations is the Lamb shift, a tiny but precisely measured difference in the energy levels of hydrogen atoms that cannot be explained by classical quantum mechanics, but falls naturally out of quantum field theory when vacuum fluctuations are taken into account. The Lamb shift was first measured by Willis Lamb and Robert Rutherford in 1947, and its explanation was one of the early triumphs of quantum electrodynamics, the quantum field theory of electromagnetism. These are not exotic or marginal effects. They are precise, reproducible measurements that confirm the reality of vacuum energy at the level of everyday laboratory physics. The vacuum energy raises a profound puzzle, however, one that sits at the frontier of theoretical physics and has not been resolved despite decades of effort. When physicists calculate the total energy density of the quantum vacuum from first principles using the equations of quantum field theory, they obtain a number, and when they compare that number to the observed energy density of empty space, derived from cosmological measurements, the two values do not agree. They do not merely disagree slightly. They disagree by an enormous factor. Depending on the assumptions made and the energy scales included in the calculation, the theoretical prediction for the vacuum energy density exceeds the observed value by somewhere between 40 and 120 orders of magnitude. An order of magnitude is a factor of 10. 120 orders of magnitude is a factor of 10 multiplied by itself 120 times. This discrepancy between the theoretically predicted vacuum energy and the measured value is sometimes described as the worst prediction in the history of physics. It is called the cosmological constant problem, and it represents a gap in our understanding that has not been bridged despite enormous effort from some of the most talented theoretical physicists of the past several decades. Something is wrong with our understanding, or something is cancelling out almost all of the vacuum energy through a mechanism we have not yet identified. Several proposals have been made, including the idea that contributions from different quantum fields nearly cancel each other out, leaving only a tiny residual. But no fully satisfactory explanation has been found. What we do know is that the vacuum energy is real, that it has observable effects, and that it is present everywhere. Every point in space, no matter how far from any star or galaxy or particle of matter, is threaded through with quantum fluctuations. The emptiness of the universe is not a passive backdrop. It is an active, energetic medium whose properties we are still working to understand. There is a connection here to the accelerating expansion of the universe that we touched on in earlier chapters. Dark energy, the mysterious component that makes up roughly 68% of the universe's total energy content and is responsible for the accelerating expansion of space, may be related to vacuum energy. The simplest model of dark energy treats it as a constant energy density of empty space, exactly what vacuum energy provides. In this model, as the universe expands and the volume of space increases, the total amount of dark energy increases proportionally, because more space means more vacuum energy. This would explain the accelerating expansion. As the universe grows larger, the total dark energy grows with it, driving faster and faster expansion. The voids we described in the previous chapter are not merely growing because space is expanding. They may be growing because the energy of empty space itself is pushing them apart, filling the universe with more and more emptiness as time goes on. The universe expands because the vacuum pushes it outward. The voids grow because empty space has a kind of energy that ordinary matter does not. Emptiness, in the quantum mechanical sense, is not passive. It is one of the most active and consequential features of the cosmos. There is one more aspect of the quantum vacuum worth considering before we move on, and it connects the very small to the very large in a way that is easy to overlook. The quantum fluctuations of the vacuum are not merely a feature of the present universe. They played a role in shaping the universe from its very beginning. During the period of inflation we discussed in Chapter 3, the extraordinarily rapid expansion of the early universe stretched quantum fluctuations in the vacuum to cosmic scales. What began as microscopic variations in the energy density of empty space, fluctuations so small that they would normally annihilate almost immediately, were stretched by inflation to scales large enough to influence the distribution of matter across the entire observable universe. Those stretched fluctuations became the tiny variations in density that we identified in Chapter 3 as the seeds of all cosmic structure. The filaments of the cosmic web, the galaxy clusters, the voids, the entire large-scale architecture of the universe, all of it traces back to quantum fluctuations in the vacuum of the early universe, amplified by inflation to cosmic scales. The largest structures in the observable universe, spanning hundreds of millions of light-years, originated as quantum events smaller than a subatomic particle. The emptiness that dominates the cosmos, the vast voids between galaxy clusters, grew from seeds planted by the fluctuating energy of empty space in the universe's first moments. This connection between the quantum vacuum and the large-scale structure of the universe is one of the most remarkable in all of science. It means that the emptiness we observe at the largest scales and the activity we observe at the smallest scales are not independent phenomena. They are part of the same story, connected through the history of the universe and through the fundamental principles of quantum mechanics. We began this chapter with the assumption that empty space would be the simplest thing in the universe to describe, a true void, an absence of everything. What we found instead is that the closer you look at emptiness, the more complex and surprising it becomes. This has been a theme throughout our exploration tonight. Every time we have approached the question of emptiness from a new direction, we have found that it is richer and stranger than it first appeared. The distances between stars are vast, but they are not featureless. The voids between galaxy clusters are enormous, but they are threaded with dark matter. The space inside atoms is mostly empty, but it is governed by forces and principles that give rise to everything we experience as solid and real. And the vacuum itself, the ultimate empty space, turns out to be filled with fluctuating energy and spontaneous activity. There is one more layer to this story, and it is perhaps the most personal one. Chapter 8. What emptiness means for us. We have traveled a long way tonight. We began with a simple observation, that most of space is empty, and followed that observation through layers of increasing depth and strangeness. We looked at the distances between stars and found them almost incomprehensibly vast. We looked at the structure of the universe and found it dominated by voids. We looked inside matter itself and found that the atoms composing everything we have ever touched are overwhelmingly empty space. We looked at the quantum vacuum and found that even the emptiness is full of something, a ceaseless fluctuation of energy that underlies all of physical reality. Now it is worth stepping back from the physics and sitting with what all of this means, not just as a scientific description of the universe, but as something we carry with us as the people living inside it. The first thing to notice is that the emptiness is not a problem to be solved. It is not a deficiency in the universe, a sign that something is missing or that things went wrong somewhere along the way. The emptiness is the result of the universe following its own rules with extraordinary consistency over an extraordinary length of time. Expansion stretched space. Gravity gathered matter into structures. The structures left voids behind them the way a river carves channels through a landscape, not destroying the surrounding terrain, but reshaping it, leaving some regions full and others bare. The emptiness is as natural a feature of the cosmos as the galaxies themselves. There is something quietly reassuring in that. The universe is not incomplete. It is not waiting for something to arrive and fill its silences. It is exactly what the laws of physics, operating over nearly 14 billion years, produced. The vast silences between stars are not absences. They are part of the shape of things. The second thing worth considering is what the emptiness reveals about the nature of existence itself. We tend to think of things as primary and space as secondary. Objects are real. The gaps between them are just gaps. But the universe suggests a different perspective. Space came first. The quantum vacuum, with its fluctuating energy and its fundamental uncertainty, preceded matter. The universe began not as a collection of objects in a container, but as a set of conditions from which objects eventually emerged. Matter is, in a sense, a local departure from the default state of the cosmos, which is something closer to emptiness than to fullness. This perspective has deep roots in physics. In quantum field theory, particles are not the primary constituents of reality. Fields are, and fields exist everywhere, in the vacuum as much as anywhere else. What we call particles are disturbances in those fields, temporary concentrations of energy against a background that is always present, always active, never truly still. Matter emerges from the vacuum. It does not precede it. This does not diminish the significance of matter or of the extraordinary complexity that has emerged from it. Stars, planets, oceans, ecosystems, minds capable of wondering about the nature of the cosmos. All of these are remarkable precisely because they are so improbable against the backdrop of an overwhelmingly empty universe. The rarity of matter is part of what makes its organization into complex structures so striking. Think about what had to happen for complex structure to exist at all. The universe began in a state of near-perfect uniformity. The matter that existed was spread almost evenly across an expanding space, with only the faintest variations in density from one region to the next. Those variations, as we discussed, were seeded by quantum fluctuations stretched to cosmic scales during inflation. They were extraordinarily small, differences of only 1 part in 100,000 in the density of the early universe. From those tiny seeds, gravity built everything. Over hundreds of millions of years, the slightly denser regions attracted more matter. Gas clouds collapsed. Stars ignited. The first generations of stars lived fast and died violently, seeding the surrounding space with the heavier elements forged in their cores. Those elements, carbon, oxygen, nitrogen, iron, all the constituents of chemistry and biology, did not exist in the early universe. They were manufactured inside stars and scattered across space by stellar explosions. Second and third generation stars formed from this enriched material, surrounded by disks of gas and dust that coalesced into planets. On at least one of those planets, in at least one solar system, in at least one galaxy among 2 trillion, the chemistry of carbon and water and energy gradients gave rise to something that had never existed before in the history of the universe as far as we know. Life. And from life, over billions of years of evolution, something even stranger emerged. Awareness. The capacity to observe the universe, to measure it, to build instruments sensitive enough to detect the faint glow of radiation left over from the first moments of cosmic history, to map the distribution of galaxies across billions of light years, to infer the existence of matter that cannot be seen, to calculate the energy of empty space from first principles. The universe became, in at least one small corner of itself, capable of asking questions about its own nature. Consider for a moment what had to happen for you, specifically, to exist. The matter in your body was forged in the cores of stars that lived and died before the sun was born. Those stellar remnants drifted through the interstellar medium for millions of years before being gathered into the cloud of gas and dust that eventually collapsed to form our solar system. The atoms that make up your body have traveled unimaginable distances across an almost entirely empty universe, passing through stellar furnaces and interstellar voids before finding their way into the particular arrangement that constitutes a living, thinking person, lying quietly in the dark. Each of those atoms is itself mostly empty space, held together by forces operating at scales so small they have no everyday equivalent, governed by principles that allow solidity to emerge from near nothingness. The carbon in your body was synthesized in the interior of a red giant star through a process so improbable that it requires a precise alignment of nuclear energy levels that the physicist Fred Hoyle predicted must exist before it was confirmed experimentally, because without it, carbon could not form in sufficient quantities for life to exist, and he was alive to notice. The iron in your blood was forged in the final moments of a massive star's life, scattered across space by a supernova explosion, gathered by gravity into the solar nebula, incorporated into the Earth as it formed, cycled through the geochemistry of a young planet, taken up by the first living organisms, passed through billions of years of biological evolution, and eventually found its way into the hemoglobin molecules carrying oxygen through your body right now. You are, in the most literal sense, made of stars, and you are resting in a mostly empty universe that had to be exactly as empty as it is for any of this to be possible. This is not a poetic embellishment. It is a physical argument. The emptiness of the universe is not incidental to our existence. It is a precondition for it. Stars form because gravity can gather diffuse gas clouds into dense, hot cores when nuclear fusion ignites. This process requires that matter be spread thinly enough across space that the clouds can collapse under their own gravity without immediately colliding with neighboring clouds and disrupting the process. Too dense a universe would not form stable stars. It would form something else entirely, perhaps a uniform plasma that never condensed into the discrete structures that make stellar nucleosynthesis possible. Planets form from the debris of stellar evolution, the dust and gas left over after a star ignites and blows away the excess material from its forming disk. This process requires time, and time requires the slow expansion of the universe to provide stable conditions over billions of years. A universe that collapsed back on itself too quickly, or expanded too rapidly for gravity to gather matter into structures at all, would not produce planets. Life, as far as we know, requires liquid water, which requires a planet at the right distance from a stable star, which requires a solar system that formed from the right mix of elements, which requires multiple generations of stellar evolution, which requires billions of years, which requires the universe to be old enough and stable enough to allow all of this to unfold. The emptiness, the vast distances, the slow expansion, the billions of years of cosmic time, all of it is part of the same package. You cannot have the emptiness without the time. You cannot have the time without the expansion. You cannot have the expansion without the physics that produced it. And you cannot have life, at least not life as we know it, without all of the above. The universe had to be almost entirely empty for almost incomprehensibly long periods of time for this quiet evening to be possible. There is something else worth sitting with, something that the exploration we have conducted tonight suggests, but does not state outright. We have looked at emptiness from many angles, and at every scale we have examined, the emptiness has turned out to be less simple than it appeared. The void between stars contains a thin interstellar medium. The void between galaxies contains sparse gas and dark matter. The void inside atoms contains electromagnetic forces and quantum probability clouds. And the ultimate void, the quantum vacuum itself, contains the ceaseless fluctuation of energy that underlies all of physical reality. There is no emptiness that is truly empty. There is no silence that is truly silent. Even the most remote region of the most isolated cosmic void is threaded with quantum fields, dark matter halos, the faint echo of the cosmic microwave background, the stretching of space itself driven by dark energy. The universe does not do nothing. Even where it appears to contain nothing, it is doing something. Even the most barren stretches of intergalactic space are participating in the expansion, threading with fields, fluctuating at quantum scales, carrying the imprint of everything that has happened since the first moment. This is not a mystical observation. It is a physical one. But it does carry a kind of quiet significance. The emptiness we perceive in the night sky and in the spaces between things is a surface impression. Underneath it, at every scale, there is structure, there is activity, there is a universe that is never entirely at rest, never entirely absent, never truly nothing. The distances are real. The silence between galaxies is real. The atoms of your body are real in their near-nothingness. And so is the fluctuating energy of the vacuum, the dark matter scaffolding of the cosmos, the ancient light of the cosmic microwave background still traveling through space 13 billion years after it was released. All of it is here, in this mostly empty universe, present and active and stranger than it first appeared. There is nothing more to understand tonight. We have followed the question of emptiness as far as it will take us in a single evening, from the distances between stars to the fluctuations of the quantum vacuum, from the formation of cosmic structure to the conditions that made your existence possible. What remains now is simply to rest inside the vastness of it. And yet here we are. That phrase is easy to pass over quickly, but it deserves a moment of attention. Here we are, not as a statement of simple presence, but as a recognition of improbability. The conditions required for our existence are so specific, so dependent on the universe having exactly the properties it has, that the fact of our being here to notice any of this is itself one of the most remarkable features of the cosmos. Physicists and philosophers have long grappled with what is sometimes called the fine-tuning problem. The fundamental constants of nature, the strength of gravity, the mass of the electron, the energy of the vacuum, the rate of expansion of the universe, All of these have specific values, and in many cases, if those values were even slightly different, the universe would be radically different in ways that would preclude the existence of stars, planets, chemistry, or life. If the strength of gravity was slightly greater, stars would burn through their fuel too quickly for planetary systems to develop complex chemistry over billions of years. If it was slightly weaker, gas clouds might never collapse into stars at all. If the energy difference between the bound and unbound states of certain atomic nuclei was slightly different, the carbon-producing process inside red giant stars would not work, and carbon, the foundation of all known biochemistry, would be vanishingly rare in the universe. These observations do not prove anything in particular about the universe's origin or purpose. Physicists are careful about that. The fine-tuning of the constants could have many explanations, including explanations that do not invoke any special significance for life at all. Perhaps there are many universes with different constants, and we inevitably find ourselves in one compatible with our existence, because we could not exist in the others. Perhaps the constants are related to each other through physics we do not yet understand, and their values are less arbitrary than they appear. Perhaps the appearance of fine-tuning is a consequence of how we frame the question, rather than a genuine feature of the universe. None of these possibilities can currently be confirmed or ruled out. The fine-tuning observations are real. Their interpretation remains open. What can be said without overstepping is this: the universe we inhabit has properties that allow for the existence of complexity. The emptiness is one of those properties. The slow expansion, the billions of years of cosmic time, the thin distribution of matter that allows stars and planets to form in relative isolation, the quantum fluctuations that seeded the cosmic web. All of these features of the universe contribute to the conditions that made our existence possible. Whether that means anything beyond the physics is a question that science alone cannot answer. But the physics is remarkable enough on its own. Let us return for a moment to the scale of what we have been discussing tonight, and sit with it from a slightly different angle. The observable universe is roughly 93 billion light-years in diameter. Within that volume, there are approximately 2 trillion galaxies. Each galaxy contains, on average, hundreds of billions of stars. Around many of those stars, planets orbit. On at least one of those planets, life exists. On that planet, a species evolved that developed the capacity for abstract thought, for science, for mathematics, for the kind of sustained inquiry that can trace the history of the universe back to its first moments and forward to its ultimate fate. And that species, on this particular evening, is lying quietly somewhere on the surface of a small rocky planet, orbiting an ordinary star in one of the outer arms of a spiral galaxy, listening to the story of the universe that produced them. The scale of the cosmos has a way of making human concerns feel small. The distances are so vast, the timescale so long, the number of stars so enormous, that it can seem as though our existence is an inconsequential detail in an overwhelmingly large and indifferent universe. That feeling is understandable. The numbers do not lie. We are small, and the universe is very large. But there is another way to hold the scale, one that does not require diminishing either the vastness of the cosmos or the significance of what has emerged within it. The universe is large because it is old. It is old because the physics that governs it allows stable structures to persist over billions of years. Those stable structures, stars and galaxies and planets, are the preconditions for everything that followed. The size of the universe is not a backdrop that dwarfs us. It is the context that produced us. We are not small against a universe that is indifferently large. We are here because the universe is as large as it is. The 14 billion years that separate us from the Big Bang were not wasted time. They were the time required for hydrogen and helium to become everything else, for the first stars to form, live, and die, for the heavy elements to be scattered across the galaxy, for second-generation stars to form with rocky planets, for the chemistry of life to begin, for evolution to produce the complexity of living systems, for one branch of that evolution to develop the capacity for wonder. 14 billion years is what it takes. The universe is exactly as old as it needs to be. And in that time, in that vast and mostly empty space, the matter that exists organized itself into structures of increasing complexity. Atoms became molecules, molecules became cells, cells became organisms, organisms became ecosystems, and somewhere in that long chain of increasing complexity, matter became aware of itself. That is what we are. Matter that has become aware of itself. Atoms that have organized themselves into a configuration capable of asking where atoms come from. Empty space that has, in a small and temporary way, become curious about its own emptiness. There is a particular kind of peace that can come from holding this perspective. Not the peace of indifference, of deciding that nothing matters because everything is so vast, but the peace of proportion, of recognizing that we exist at the right scale, in the right place, at the right time, inside a universe that had to be exactly what it is for any of this to be possible. The vast silences between stars are not lonely. They are patient. They are the space through which light travels for billions of years, carrying information about the universe's history to any instrument sensitive enough to receive it. They are the room that gravity needs to do its slow work. They are the backdrop against which the rare and extraordinary event of complexity can occur. The emptiness is not a negation of our existence. It is its precondition. One last thought before we move toward rest. We have spent this evening exploring emptiness at every scale, and at every scale we have found that what appeared to be nothing turned out to be something. The void between stars contains the thin medium through which stellar winds travel. The void between galaxies contains dark matter and sparse gas. The void inside atoms contains the forces that give matter its properties. The quantum vacuum contains the fluctuating energy that underlies all of physical reality and drove the expansion that shaped the universe from its earliest moments. There is a pattern in this. Every time we looked more carefully at emptiness, we found that it was not empty at all. It was simply full of things we had not yet learned to see. This pattern may continue. There may be aspects of the vacuum, of the dark components of the universe, of the nature of space itself, that we have not yet discovered. The history of physics is largely the history of finding structure in what was previously thought to be featureless. The atom was once thought to be the indivisible, structureless unit of matter. Then the nucleus was discovered inside it, and electrons around it, and quarks inside the nucleus, and gluon fields binding the quarks. Each layer of apparent emptiness turned out to contain another layer of structure. It would be surprising if that process had come to an end. The universe is mostly empty, but the emptiness, it turns out, is one of the most interesting things about it. Not because it is nothing, but because it is never quite nothing. Because every apparent void contains, on closer inspection, a quiet complexity that rewards attention. Closing. The universe is mostly empty. We have sat with that fact tonight from many different angles, and somewhere along the way it may have changed shape. What began as a simple observation, a statement about the distances between things, became something richer and stranger the longer we stayed with it. We began with the spaces between stars and found them so vast that even light, the fastest thing in the universe, requires years to cross them. We followed those distances outward through the galaxy, through the local group, through the filaments and superclusters of the cosmic web, until we arrived at the great voids, regions of space hundreds of millions of light years across, containing almost nothing at all. We found that those voids occupy the majority of the universe's total volume, that the galaxies and clusters we can see are not the fabric of the cosmos, but the thin, luminous threads running through it. We turned inward and found the same pattern waiting for us. The atoms that compose everything we have ever touched are themselves almost entirely empty, their apparent solidity a consequence not of matter packed tightly together, but of invisible forces operating across near nothingness. The nucleus of a hydrogen atom occupies so small a fraction of the atom's total volume that scaling it up to the size of a marble would leave the boundary of the atom nearly a kilometer away. The solidity of the world is an emergent property of emptiness governed by rules. We looked at what fills the spaces that ordinary matter leaves behind and found that the universe contains far more than meets the eye. Dark matter, 5 times more abundant than the matter we can see, provides the invisible scaffolding along which galaxies form and the cosmic web is organized. Its identity remains one of the deepest open questions in physics, detected everywhere through its gravitational influence and nowhere directly. And then we looked at the emptiness itself, at the quantum vacuum, and found that it is not empty at all. It is the lowest energy state of all the quantum fields that permeate space, and that state is one of ceaseless fluctuation. Virtual particles flicker in and out of existence. The Casimir effect pushes metal plates together in a vacuum. The zero-point energy of empty space may be driving the accelerating expansion of the universe itself. The quantum fluctuations of the early vacuum, stretched to cosmic scales by inflation, seeded the entire large-scale structure of the cosmos. The emptiness that dominates the universe is, at every scale, full of something. We considered what all of this means for us, and found that the emptiness is not incidental to our existence, but essential to it. Stars form because matter is spread thinly enough across space to collapse under gravity into discrete burning spheres. Planets form from the debris of stellar evolution. The heavy elements that make chemistry and biology possible were forged inside stars and scattered across the galaxy by supernovae. The billions of years required for all of this to unfold were made possible by the slow, patient expansion of a universe that began almost incomprehensibly hot and dense and cooled over cosmic time into something that could harbor complexity. You are here because the universe is mostly empty. You are made of matter that traveled through that emptiness for billions of years before arriving at this particular arrangement. The atoms of your body were forged in stellar interiors, scattered by explosions, gathered by gravity, assembled by chemistry, shaped by evolution, and organized by the same physical laws that govern the quantum vacuum and the rotation of galaxies. At every scale, from the largest voids in the cosmic web to the spaces within the atoms of your body, the universe is defined more by absence than by presence. And yet, within that absence, structure persists. Complexity emerges. Matter organizes itself into forms of increasing intricacy over vast stretches of time. We exist at the intersection of all of this. Brief concentrations of matter in a universe that strongly prefers to be empty. Temporary arrangements of atoms that arose from the vacuum, as everything does, and will eventually return to something closer to the universe's default state. And in the time between, aware, capable of wonder, capable of looking out at the overwhelming emptiness and finding it, not frightening, not lonely, but quietly remarkable. The distances are real. The silence between galaxies is real. The quantum vacuum is real, and its fluctuations are real. And the dark matter threading through the cosmos is real. And the ancient light of the cosmic microwave background is still traveling through the emptiness right now, 13 billion years after it was released. All of it is here, present and patient and stranger than it first appeared. There is nothing more to understand tonight. The universe will continue its slow expansion while you rest. The voids will grow by distances too small to measure in a human lifetime. The quantum vacuum will continue its patient fluctuation beneath the surface of everything. The stars will go on burning in the dark, scattered thinly across an almost incomprehensible expanse of nothing, each one a temporary concentration of matter in a universe that is learning, slowly and in small places, to notice itself. You are resting in a small, warm corner of a mostly empty universe. The emptiness surrounds you on every scale, from the spaces between the atoms of the surface beneath you to the vast silences between the nearest stars. It has always been there. It will remain long after the last star burns out and the last black hole evaporates and the cosmos settles into its final, cold, quiet state. And right now, inside all of that emptiness, you are here. That is enough.